Morning, Science 30s. I just wanted to make a few notes on the section 2.3, Understanding Exposure. I just posted it, and I will just go through some of the questions and cover some of the vocabulary. And then, obviously, your next step after this is to start reviewing all of Chapter 2. So, there's a couple of terms that I've just listed and compressed in here. Um, Obviously, what we're really trying to understand here is the risk of being exposed to harmful substances and how we can analyze those amounts. Uh, One thing that can happen with different materials is something called off-gassing. That's this first term here. And all that really means is there's some organic compounds. They call them volatile organic compounds, or VOCs. Um, They are emitted from substances like paint, for example, which you can smell, or new carpet if you can smell it, or when you smell it. Those are those can be volatile organic compounds. So that obviously is a part of indoor air quality. So if you have a lot of these in the materials that are in a room, then you could be more exposed to them, obviously. So there's other volatile organic compounds, but that's one thing to be aware of just indoors. If we go outdoors, uh, the more common consideration there is our pesticides. So pesticides, I'm sure you've heard of. Loosely, you should be familiar with the different kinds. There's insecticides, herbicides, and fungicides. Maybe it's fungicides. I'm not sure how they pronounce that. Anyway, you can see the root word, though it's kind of easy to tell, either dealing with insects or plants or herbs, and then or fungus. So when farmers use pesticides, there's kind of two general categories in reference to what's called target specificity, in terms of if you have a high target specificity, it just means you're focused just on one, uh, even one insect sometimes, or one weed. And a very common, considered a high target specificity organic compound is 2,4-D. I think I've even used this in some of the homes I've lived in to kill dandelions. It's a very common, um, I guess you could call it a herbicide because it's unwanted plants, but generally it just falls, we just call it a pesticide. So there's a picture of it there, 2,4-D. You'll notice that it has this carboxylic acid on the end, and that means that it can form esters. That comes up a little bit later. But uh, a broad, so you have, in terms of specificity, you can have high or low target. So that's kind of what both of those two terms deal with. And we've already alluded to this a little bit, but you should just know that generally toxicity is the ability of a substance to do any of these things here. So just, damage to living tissues, problems within any body system, and even death. So that's not a good one. Obviously, most materials can be toxic at certain levels. So you get too much of anything, it's not good. Uh, Two expressions you should be familiar with because they'll be referenced a lot are LD50 and LC50. They'll be written just like that, with the 50 being like a subscript, and they refer to either lethal dose, so a dose that can kill you, or lethal concentration, a concentration that'll kill you. The 50 is just a statistical separation because we're curious, um, with these lethal doses or concentrations, if they kill half of the population. I mean, obviously, if they kill 100%, that's really bad. So, uh, obviously, we're trying to determine how harmful certain organic compounds are, and especially if they're harmful to organisms, then they could potentially be harmful to us. So that's why we study them. If animals and plants are dying off, then there's a possibility that we might be next. So you'll see reference to LD50 or LC50 in some of the questions. And yeah, there's a table there I posted that just shows some examples. They either list them in milligrams per liter, so that's how much of the compound there is per liter of water, or maybe it's per kilogram of soil or per kilogram of mass of the the organism. So uh, the questions that I have asked here are, what's the advantages and disadvantages of using a pesticide that can only kill one or can kill many? I think you guys can see that okay. I kind of answered it down here. Obviously, if you only have one insect that you're dealing with, then you can target just that insect and take care of it, and you won't be harming additional insects or organisms when you use that pesticide. But sometimes there isn't just one insect that's causing the problem. Maybe there's multiple insects, or maybe there's multiple plants. It isn't just one plant. So you need to use a broader spectrum pesticide. Okay. So just for a quick example, you could see this. Scientists were testing 2,4-D and an ester of 2,4-D to see what their lethal concentration is, their LC50 is. So you can see the data pretty quick. And I think for a standard question, you just have to interpret the numbers and see. So, in this case, it says which substance has the greater toxicity. Well, it looks pretty obvious from these numbers here that the 2,4-D has a much higher kind of concentration in milligrams per liter basically in every case in both the rainbow trout and the Chinook salmon. So I don't think you'd have too much difficulty interpreting the data from a graph like that. In part B, why would experiments be performed to determine these values for a variety of organisms? I mentioned that a bit already. We really want to know if it's going to be harmful to us down the road. Yes, we want to prevent unnecessary death in any organisms. I mean, obviously, the health of an ecosystem relies on all of the contributing factors. And if we start throwing pesticides in there, usually when we start messing with nature, usually we make it worse. And so, but yeah, ultimately, we really want to know if it's going to hurt us. And then part C, I kind of already answered that. If you look at the structure, I'll just back up a little bit. If you again look at this structure, you can see that for 2,4-D, it's got the carboxylic acid group that could easily react with an alcohol, and if you remove water, then you can pull water out, if you remember from our other notes, and then basically this H would disappear, and then this would be connected to another carbon, which could then be connected to some other things, and we would make an ester. So anytime you're asked about an ester, what you're really looking for is this group that I've already circled, the COOH group. That's a carboxylic acid, and yes, it can react with an alcohol, probably with some other things too, but it can definitely react with an alcohol, and it can make an ester. So considerations of using pesticides, there's a lot of these have to do with actually distributing the pesticides. I put the first one here, combined effects. It just means that often pesticides, they're made of a bunch of compounds instead of just a single pure chemical or pure substance. So levels of toxicity could be altered because those compounds might interact with each other or interact with other things. Drift is a fairly straightforward one. Like if you spray a field, can you guarantee that pesticide will just stay in the field? No, because the wind can blow it to the next field, and that might have something else in it. And so in similar fashion to drift, there's something called the grasshopper effect. And this one's a little more interesting because basically the pesticide will be dumped onto the ground or whatever, and all of it maybe isn't absorbed by the plants or by the organisms. So in a warm climate, it can evaporate. So it's a liquid going down, so it can evaporate into a gas. And then it can be transferred by winds to a cooler climate, or where it gets up into the atmosphere. Then it can condense and actually turn back into a liquid, and then it can fall down as rain. So that way it could actually, they call it grasshopper because it basically it'll come up for one area and go a great distance and then fall back down in another area. So like way away from where you first sprayed it. And one of the major concerns is that, and you'll see that in the other ones, is that our wind patterns on the Earth tend to carry those compounds closer to the poles. We have what's called the polar vortex. It's just a series of wind currents. And so what's happening is organisms in the Arctic, at least in our region, are seeing higher levels of these compounds because they're getting there. They're actually making it there because of this grasshopper effect. Now, another term you should know is something called persistence. And in general, and this is the real danger of the halogenated hydrocarbons. Okay, so that's having, the chlorine, the fluorine on these hydrocarbon chains, are also the benzene rings. These benzene rings, you see them drawn like this, they're just really stable. They tend not to be broken down very well by biological or even chemical means. You got to really crank up the temperature high. I mean, you can get it. I think I was reading it was over 1,000 degrees Celsius is needed to kind of break these up, and that doesn't happen in nature very often. And if you also have, if you have an alcohol group just sticking off of a benzene ring, something like this, these are called phenols. And you'll see that a little later in the notes. But if you see that prefix phen, P-H-E-N, it is a benzene ring or an aromatic ring that has an alcohol stuck on it. And it's just really stable. And that's often a problem. So persistence is where these benzene rings they just don't break down. They're persistent in their existence, I guess. It would be one way to consider it. The last part's on the effects on water quality. So these compounds, how can they affect our water quality? I think we're all familiar with fertilizers, but the main thing, fertilizers just have a bunch of nutrients in them that are really going to be helpful for plants. And that can be a problem if it gets into the water system, because organisms that we really don't want to be growing out of control can grab those nutrients and use them. And another component you'll see is organic matter. So organic matter, that's just waste or decaying material from plants and animals. What happens is that that needs to be broken down, or it will be broken down by bacteria and other organisms. And if you have a lot of organic matter that can be broken down, those bacteria and organisms will go crazy trying to break it down, and they will essentially steal a whole bunch of oxygen to do that. And so I'm kind of jumping the gun a little bit, but hopefully you're familiar with what algae is. It's just it's a very small microorganism. Basically, it's a plant, but algae will rapidly increase if there's a whole bunch of extra nutrients in the water, and that comes from all the fertilizers. Like as the rainwater washes fertilizer off of a farmer's field, it gets into the water system. So sometimes it's also from leaching. I guess I said that too. It's also from leaching. So runoff or leaching is where those nutrients will get into the water system. And if you've ever seen a pond, like a pond or a body of water it's full of like green slime, that's the algae, and it's just been growing out of control. Well, not out of control, but it's just growing because all the nutrients are there. So those bodies of water are called eutrophic. That's another term you might see. It just means it has excessive plant growth due to all these nutrients there. So as we mentioned earlier, toxins are anything that's harmful. And in terms of water, toxins are actually made by the algae. So this algae that's growing like crazy, they produce toxins themselves. And so, That's why if you go swimming in a pond, you can get a rash. I've never done that, but or I mean, if you go like wade in a pond or like a still body of water where the algae are largely present, yeah, it can cause a rash. Um, so, but that's probably not surprising based on the fact that there'd be toxins in there. So something else happens though if there's less and less oxygen in the water because of these the microorganisms, and that is that other organisms larger will now not be able to survive because there's less and less oxygen. So we call that term winter kill. So because the oxygen levels go low, then larger organisms like fish can't survive, and so they'll start dying off. And it can happen in huge amounts. Like you can have thousands of fish that just are all of a sudden die. Well, not all of a sudden, but over a short period of time they will. So when we're studying oxygen, here's another term that if you haven't seen it in your biology classes, you need to know it. It's called biochemical or biological oxygen demand, BOD. And sometimes even on test questions, they'll just say BOD and they won't say that it's biochemical oxygen demand. So I have just a picture of a bottle that is a standard kind of glass bottle that's used for this test. But it's really a simple test. If you see BOD, what it means is you take a sample of the water and then you seal it off. So you take the sample, seal it off. Well, actually, sorry, you take the sample, you measure how much oxygen, dissolved oxygen, is in that sample to start, and then you seal it off and you wait for like 5 days. That's like a standard time. Then after 5 days, you go back to the sample and you analyze how much oxygen there is now. And in that water sample, as you can see, obviously there'd be bacteria, oxygen, and all those other things are in there. The bacteria largely and other organisms that are there, they will use up oxygen because it's there. And then obviously there's a limit because after a while they can't do anything. But if there's lots of those organisms and in your sample, then the amount of oxygen will obviously go down. So as I mentioned there, any sample that has high levels of organic matter. See, so organic matter is just dead and dead plant matter that is kind of basically food for these bacteria. Okay, so it'll also, if it's high levels, then that means it's going to have a high BOD. Now that's a little, high BOD means there's a high demand for oxygen because the bacteria need it. So what it really means is just that high BOD means that the oxygen levels will go down at the end of the 5 days. So if there's a high BOD, you'll see a lot of the oxygen will be depleted after that time. One of the sources of this organic matter is actually sewage, and obviously, animals that are, like you got a field of cattle out there. There could be some of as any of that washes, any of the waste washes into the water system, then you can have a problem. But you're also worried about other things like dangerous bacteria like E. coli. So sewage, of course, is controlled, but in a water system, that's the last thing you want to be getting in your water system is sewage, at least the drinking water system. So just the last few things here. We already talked a bit about persistence. Resistance is very similar. Resistant populations, this is very much the same as we studied with bacteria, with DNA. For the same reason that bacteria can get resistant, just organisms can too. So you have to watch out that actually really aggressive pesticides can actually speed up the amount of resistant populations. So the classic example is something called warfarin in the 1950s. This was warfarin was used to kill rodents, and it actually developed. Some rodents survived the warfarin, like they would eat it and it wouldn't kill them, and then they would reproduce, and then their offspring were like super resilient to warfarin, and to the point that it was almost useless in killing off rodents from that point on. So that's a factor that you have to consider when you are kind of producing organic compounds, especially to kill pests. So in general, this was just a note here. Just make sure you reduce your exposure to wear the proper clothing so you're not, and also follow safe handling procedures so you're not getting exposure. And yes, we always test our water to ensure that we're not getting chemical or other substances that are harmful. You should be familiar with the concept that the shape of a toxin can also sometimes mimic the effects of another one. This was just one example that the text pulled out. Estrogen is obviously a naturally occurring compound that all organisms produce, and that's this shape that's at the top here. There's two basically compounds that they mimic that shape largely because of their benzene rings, and also that they're either halogenated rings, as in that first one, the TCDD compound, or this bisphenol A has also some phenol group. So there's the phenol group that I was mentioning earlier, just an OH group stuck off of a benzene ring. But what's crazy is both of these two actually mimic estrogen, so they can disrupt like reproductive cycles, fertility, and behavior if the doses are high enough. So not surprising that if the shape of the pesticide is similar to something else, then it can kind of act like it, which is that can be dangerous. So, and then the last part here, farmers usually take a wide variety of approaches against pests. They're usually not only using chemicals. So as listed here, you can use natural predators, biological agents. You can use crop varieties. So the pests, if you keep swapping the crops in a field, the pests can be deterred a little bit because it's not the same crop every time. And yes, sometimes you can flood or burn the growth to like eliminate eggs and the capacity for the pests to come back the next year. And they try and only use pests when absolutely necessary. So here's some others, of course, like tilling and planting alternate crops. What we're really avoiding, or what we hope to try and avoid, is again this other acronym, POPs. Those are persistent organic pollutants. These are the guys that have like the benzene rings and the halogenated hydrocarbons. We want to try and minimize those as much as possible. The reality is these are in a lot of the pesticides that are used, but we just try and monitor them and come up with ways to minimize their impact on the environment. And the text comes up with something, they call them the dirty dozen, the 12 POPs that have been detected in Arctic food chains. Now, again, that's because, due to the grasshopper effect and drift and things like that, these compounds are making their way up into the northern regions from the polar winds. And so there's higher concentrations of these in the Arctic food chains, if you will. So out of this list, you don't need to have these lists memorized. I think it's worth noting the kind of the bad boys. Here's DDT. That one was in our notes from before. It was the one that is a great example of biomagnification, because as this got into the food chain, the organisms higher and higher up got greater and greater concentrations. The classic sad one is like the peregrine falcon, that this high concentration got into its body tissues, and when it laid eggs, the eggs didn't hold up. They were structurally unstable, and so all their offspring were dying, and so it had almost wiped them out. But we figured that out, and we're able to minimize the use of DDT, and then that population has rebounded. The peregrine falcon is one example I'm aware of. I'm sure there's others. PCBs, those are part of those come from oils that are used in transformers, if I've got that right. And sometimes they can be put on roads and stuff. to kind of make them hard pack instead of gravel. And but those it'd take quite a bit of that to get into the water systems and whatnot. But anyway, we're just aware of all of these. So anyway, I hope that was helpful. I'll try and post answers to the Chapter 2 review shortly, and we've got other things coming. So keep up the good work, you guys.